In this fifth lesson, I'm going to take a closer look at the failure that I had in the last video where we had an intermittent short to ground of CAN high on this passively terminated CAN network for the after treatment bus. We can see here that when the failure occurs, when we are shorted to ground or the wire-to-wire short to the NOx sensor ground actually of CAN high, we can see that CAN high and CAN low both basically went to nearly 0 volts. If I would have had the failure would have been a short to ground of CAN low, this would have been a different pattern. So I was able to determine that this is CAN high based on this failure and the history of what I've seen from this before. So here I've got the oscilloscope hooked up to a very small CAN network that I have sitting on my desk. So you'll probably notice, first off, I'll go ahead and pause. We'll take a look in. It looks like there's a lot of noise here, but if we zoom in on this, we're going to see that it really isn't that high of an amplitude. What this is, a lot of this is I'm powering this off of a DC power supply, so it's connected to the AC 120 volts, 60 hertz. So some of this is the noise, if you would, from the power supplies. My computer is also sharing that same ground. So sometimes when we do these bench setups where we're using something like the real devices. So I have a NOx sensor, I have a couple of other sensors, and the vector CAN case. So those are my small CAN network. I've got probably 10 or 15 foot of wire harness here. It's passively terminated, but basically this is it's a little more noise than you would see on a real vehicle, but it really isn't that much of a problem. I'll go ahead and pause it. We'll go ahead and prove that. I'm going to add the math channel. We'll do the CAN high minus CAN low, which is channel A minus channel B. And I'll go ahead and drag this down. And we can see that when I zoom in on this, where you see all of this noise, because this is, if you would, common mode noise, it's the same noise on CAN high and CAN low. It's a really low amplitude. So my 0 volt level is somewhere right here on this line. It really, I have a very clean looking signal, regardless of how ugly it might look looking at it on the oscilloscope reference to ground. But because the CAN transceivers reference CAN high minus CAN low, each reference to ground, and then looks at that difference in CAN high and CAN low, that common mode voltage, or that voltage that is induced or placed on both of the wires equally, it basically gets zeroed out or negated. But anyways, we can see that I have this small network. So what I'm going to do is I'm going to introduce a short to ground of CAN high. I'm going to let you see what that looks like, and then I'll introduce a short to ground of CAN low, and we'll compare those on this passively terminated network. Okay, so I'm going to go ahead and this will be a quick short. I'm going to short CAN high to ground. You can see that pattern looks really ugly. We'll go ahead and pause this and we'll take a look to see what this looks like. And if I zoom in on this, we can see that CAN high and CAN low are basically both pulled down to almost 0 volts. I do have some instances where I've got a device that's a little further away from the short, if you would, that is trying to put messages on the network. So we can see that I really don't have any intelligence here. I can see that pretty much it probably looks very similar to what we had for the NOx sensor when we saw that it failed. So this is our 0 volt reference. Previously we would have been up here at a 2.5 volt reference. But we can see here that even though I have only CAN high shorted to ground, it has also pulled CAN low down to nearly 0 volts. So in effect, it looks like both CAN high and CAN low are shorted. And we'll take a look at what causes that a little bit later on here. Okay, so now I'm going to short CAN low to ground, and we'll see what that failure looks like. So there I have CAN low shorted to ground. We'll go ahead and pause the oscilloscope. Let's take a look at what one of these traces looks like. We can see here that if I look at the difference in voltage, previously before when I shorted just CAN high to ground, I really couldn't obtain any intelligence. There was no message that I could decode or possibly get out of this. But we can see what happens. Even though we're pulling for the recessive bit, we're pulling both CAN high and CAN low down to near 0 volts because we're looking at the difference in voltage that is nearly 0 volts. CAN high, in this case, the CAN high increases up to about 3 volts, and I get a difference in voltage between, if you would, the dominant and recessive bit of about 3 volts. So believe it or not, I can decode this. I can go ahead and add the serial decoder. We'll give it a try. J1939, can high minus can low, 250K baud. We'll go ahead and increase that up to 2 volts or so, and we'll go ahead and see if we can decode it. And sure enough, I'm able to decode this message, and I can see, of course, there's my engine controller. If I go ahead and look at some of the other messages here, there is another sensor, another smart sensor, source address EB in hexadecimal, whatever that is in decimal. I'm still able for this network to still function. So I've done this on real machines and showed technicians where I had a passively terminated CAN network, large machine, 20 or more controllers on it, and short CAN low to ground, and no fault codes, no problem. Even though the pattern looks terrible like this, it still functions. It's definitely not recommended. It affects something called the signal to noise ratio. We're dependent only on CAN high, and you definitely wouldn't want to ride around and drive this machine on the road with CAN low shorted to ground. But in reality, it is functional. This is a little different with active termination. We'll take a look at that in some examples maybe later on. But with passive termination, 120 ohm terminating resistors, I cannot short CAN high to ground and have the network work. It will not work. Basically, both CAN high and CAN low get pulled to near 0 volts. However, if I short CAN low to ground, the network with passive termination still is pretty much functional. CAN high is still there, and we're looking at the difference between CAN high and CAN low. In this case, it's like 3 volts, and I used about 2 volts on the decoder, so that's pretty good. It's able to decode these messages. To try to explain that phenomena, why I have a difference when CAN high is shorted versus CAN low, why the network may still function if CAN low is shorted to ground, at least with passive termination. What I have here is I've modeled 2 CAN transceivers in Circuit Lab. So basically, these are the components that are the basic components that are inside of a CAN transceiver that are inside of every ECU, inside of every electronic control unit that's on a CAN bus. So there'll be a 5-volt supply here. I'm showing it as a switch. In reality, this would be some sort of a transistor, some sort of a FET, a driver. Have a diode so that we keep voltage from going the other way. We have a couple of resistors somewhere around this 25K value. And then we have a 2.5 volt power supply. Same thing in the other CAN transceiver. And here I have my passive termination, my 120 ohm terminating resistors. Here's my backbone, CAN high and CAN low. So in this CAN network, if I don't have either of these switches closed, the 2.5 volts is actually what you're measuring with your meter. So the 2.5 volt regulator that is in each CAN transceiver is trying to hold the CAN bus at 2.5 volts for the recessive state. So this is where that 2.5 volts comes from. It comes from a 2.5 volt regulator in each CAN transceiver in every ECU instead of every electronic control unit. So with a recessive state, we can see that it's 2.5 volts. When we're ready for a dominant state, I'll go ahead and just change these switches. We'll change them to closed, and I'll change this one to closed. In reality, both of these would be closed at exactly the same time. You can see that we took CAN high up to about 3.4 volts and CAN low down to about 1.5 volts for a voltage differential of somewhere around 2 volts, right? So this is basically a dominant bit right now. So I have one controller that's driving to a dominant. I'll go ahead and change those switches back to the state they were in. Okay, so we're back to the recessive state. What I have here is I have this designed so that these switches will automatically close at whatever it is, some period of time, 200 microseconds after I start a simulation. So we can do an AC or a time domain simulation of this. And what we're going to see is we saw that recessive state. So here's our 2.5 volts, both CAN high and CAN low. CAN high being in blue, orange being CAN low. At 200 microseconds, then both of those switches close. They're in that transceiver on the left, and we can see we took CAN high up to 3.4 volts and CAN low down to 1.5 volts. So this is basically what's occurring every time that you, when you see a dominant or recessive bit. These switches, these electronic switches, drivers, FETs, are being controlled by the CAN transceiver or the device that is controlling the CAN transceiver to either provide a dominant or a recessive bit. So if I take and short to ground, I'm going to take CAN high first, and I'm going to short CAN high to ground. We can see already in the recessive state that I've driven both meters to virtually 0 volts. So this one definitely to 0 volts, this one to about 12 millivolts, so 12 thousandths of a volt, virtually 0 volts. So we'll go ahead and simulate again. We'll take a look at what our time domain simulation looks like, and there it is. Even though the switches open or close, nothing really changes. Everything stays pretty much at 0. This line up here is 12 millivolts, so 12 thousandths of a volt, almost 0. So that's what it looks like. It's not exactly the same as what we see when I look at this with the picoscope, mainly because I have resistance in the harness, we have capacitance, things that I haven't modeled here. I've just done a very simple model. So what I'm going to do, we'll go ahead and go back to build, and I'm going to drag this down to CAN low this time. So when I ground CAN low, obviously the CAN low meter, the meter I'm showing here, has to stay at 0 volts. So we'll go ahead and simulate this, and we'll take a look at what it looks like. And it looks pretty much like what I showed on the oscilloscope there whenever I grounded CAN low. CAN low stays at near 0 volts, dominant or recessive. CAN high, however, increases up in this case to about 3.5 volts. So this is the same kind of thing that you're seeing. I see a difference in my failure depending on which CAN high or CAN low gets shorted. So as we saw, if I short CAN low to ground with this passively terminated network, there's a good chance the network's still going to function. I might not even know that I have that short to ground, other than maybe some intermittent problems. It's definitely not something we recommend, but it's terrible signal to noise ratio, meaning it's not very robust, but it's not. It's a failure that's tough to detect otherwise. So oftentimes when I'm myself in monitoring a CAN network, I still have my short of CAN low in place. I'll watch in about this type of time frame, something where I can see quite a few messages on the screen. I'll just let it sit and run and fill up the hard drive with data until I get something that happens. And you can just see that I'm getting these flashes of something. So this could be somebody's wiggling the wire harness. Oftentimes this is a very useful technique, is to have someone sit in the cab and watch the oscilloscope while somebody else is out wiggling the wire harness. And so here, I'll go back and forth between CAN high and CAN low, and we can see, boy, that really looks a lot different when it's CAN high versus when it's CAN low for the failure mode. So this is one of the tricks that I definitely use. This short to ground of CAN high or CAN low is definitely something that does occur. It can be inside of the controller itself, which is oftentimes very difficult to locate, or more often than not, it's usually something that's in the harness. So since we have a real CAN network that we're connected to, this bench network of mine, we'll take a look at some of the details here real quick, just as a quick review. We can see the acknowledge bit. So the acknowledge bit here has an amplitude of about 3.9 on CAN high and about 1 volt on CAN low, giving us a differential voltage of almost 3 volts. By comparison, the other bits are down here at about 2 volts. We can also see that there is quite a bit of noise here. And as I said, most of this is because it's the power supply in my bench and the common ground that I have for my laptop and my setup. So that does induce a lot of noise that you're not going to see on a real CAN network. But this does show you how robust CAN is. I'm still able to decode all of this. We have all of the other devices. Nobody is complaining or throwing error frames on the CAN bus, indicating that there's some message that they don't agree with, that they've misinterpreted a logic 1 and a logic 0 someplace, a dominant and recessive bit. But anyways, this gives you an idea of how robust that CAN is. So in the next video, we'll take a look at some other types of failures. We'll introduce some open circuits of CAN high and CAN low that can really, as we'll see, wreak havoc with the CAN bus. Probably a lot of the intermittent failures that you've really struggled to find throughout your career. Oftentimes those have been caused maybe by intermittent opens. Sometimes it's in the harness, sometimes it's within the controller itself, so it's not driving CAN high or CAN low. And that can really cause some problems on the bus, as we'll see. But it's one thing that you can definitely pick out with the oscilloscope. Obviously, this short to ground scenario, you could probably find this with a good multimeter if you took your time. When we start looking at the opens, your digital multimeter is not going to be of much use to you, as we'll see.